Hello everyone, welcome to Agentic RAG from Scratch series. We are building a production grade Agentic RAG system from scratch. This is episode 6. In the last episode, we did a deep dive into LangGraph. We covered concepts like state management, persistence, interrupts, all of it. If you have missed that, link is in the description. Today we take everything we learned and build it into an actual application. Let's get into it. So up until now, we have been using LangChain's core components to power our app. Today, we are upgrading that to a proper LangGraph agent. And the difference is huge. Instead of manually chaining calls, the graph manages the entire flow for us. To keep things clean, we are not touching the existing code. We create a brand new V2 folder inside the endpoints with a chat.py file inside it. This is our fresh LangGraph powered endpoint. V1 stays untouched. Endpoint accepts a chat request model, which contains two fields. A message string, which is what user typed, and a thread ID string, which tells LangGraph which conversation to load from the memory. Next, we inject graph as a dependency into our endpoint. This is where everything comes together. Three things happen here. First, we initialize a state graph with our agent state and user context schemas. These define the shape of data flowing through the graph. Second, we add the nodes, and notice we have split nodes into a separate file, clean, testable, and easy to swap later. Third, we wire up the agentic loop with conditional edge. If LLM returned a tools call, route it to tools node and loop back. If not, we are done. Exit the graph. We covered exactly how this works in the last episode. So check that out if this is new for you. Then we initialize InMemorySaver as a checkpointer and compile the graph. The checkpointer is what gives our agent memory. Every turn of the conversation gets saved and reloaded by the thread ID. Inside the route handler, we take the user message, wrap it into a human message, and return a streaming response. FastAPI streams the response back to the client as an event arrives. So the frontend starts receiving tokens immediately, not after the full response is ready. Streaming response takes stream agent events as a function, a wrapper function that we wrote that wraps LangGraph's A-stream events and formats everything into a server-sent event so that the frontend understands. Let's break down this function to better understand it. This is an async function, meaning it won't block your server while you are waiting for AI to respond. It takes three things: a compiled LangGraph graph, a list of chat messages, and a thread ID to track the conversation. The return type is async generator, means it doesn't return once. It keeps yielding string one chunk at a time, like a fire hose of data. Before we call the graph, we package two things. The config carries the thread ID. LangGraph uses this for memory, so it knows which conversation history to load. The inputs are actual messages we are sending to the agent. Next, the event loop. This is where the magic happens. Instead of graph.invoke, which waits for the full response, astream_events fires an event for every single thing that happened inside the graph. A token generated, a tool called, a node finished. We read the event property of the event object to know which thing has just happened. Next, we'll be handling LLM text tokens. Every time the LLM generates a single token, like a word or a part of a word, this event fires. We extract the text, normalize it because LangChain can return content as a plain string or a list of objects, and then we yield it. Yield is key here. It immediately pushes the token to frontend without waiting for the rest. That's what creates typewriter effect you see in ChatGPT. Next, we are handling tool calls. When the agent decides to call a tool, like searching the web or checking the weather, two events fire: on tool start and on tool end. On tool start tells the frontend, hey, I'm calling this tool with these inputs right now, so that we can show a loading spinner. Then on tool end fires when the tool finishes and returns a result. This is how you build that UI where you are seeing a searching web before the final answer appears. Then we add the error handling part. If anything goes wrong inside the stream, network error, tool crashes, LLM timeouts, instead of silently dying, we catch it and yield an error event back. The frontend receives this just like any other event, so you can display a proper error message to user instead of stream just stopping. Finally, the final block. The finally block runs no matter what, success, error, or even in case of user cancels the request. We send a done signal, which is standard SSE convention telling the frontend the stream is over, stop listening. This is how your frontend knows to remove the loading spinner and mark the message as complete. So to put it all together, we have created a V2 to route that takes chat request model as input and graph as dependency, and calls our stream agent events wrapper function, which handles LangGraph events and stream response back to frontend in server sent events format. Now let's look at our frontend setup. In our React frontend, we have created a new hooks folder and created a new hook use stream. This is a custom React hook that powers the entire chat UI. Everything from sending a message, streaming tokens, tracking tool calls, and handling errors. This hook exposes 5 things: the list of messages to render, a loading flag, a function to send a message, a function to stop midstream, and a function to clear the chat. So we have 2 pieces of state, the messages array which drives the UI, and a loading boolean. Next, we have an abort ref. It just holds a reference to abort controller. So we can cancel the stream from anywhere without triggering a re-render. We also attach an abort controller so that whenever user enters stop, we will be able to terminate the network call. Next, we listen to the response. Instead of response.json, which waits for everything, we grab a readable stream reader. Reader.read returns a chunk of raw bytes as they arrive, not full message. Text decoder converts those bytes to a string. Then we split on new lines to get individual SSE lines. This while true loop keeps running until the server closes the connection. We have 3 event types that we wanted to handle. Text, append the token to the existing content 1 character at a time, building a response live. Tool start pushes a new tool call object into the array with status running, so the UI can show a spinner. Tool end, find the same tool call by name and flip its status to done, and attach the output. Notice we matched on both tool name and status running. If the same tool is called twice in a response, we only update one that's still in progress. Now in the main page, we import the useStream hook and use it to wire our elements. On click of send or enter, we trigger send message from the hook. We get the messages and loop over and render our chat message component. In the chat message component, we check if the tool calls are present and render the custom tool block component for each tool. Let's run both frontend and backend and see things working end to end. I will send a simple hi to the agent and look at that. It responds asking if I would like to fetch my profile information. It already knows what tools it has access to and it's offering to use them. We haven't told anything yet. That's the system prompt and tools definition doing their job. Now let's ask something more interesting. What car am I driving? The agent thinks about it, decides it doesn't have information yet, and makes a tool call to get it. You can see that renders right here on the UI. The tool call fires, we show it in real time, and once it comes back from the model, reads the result and answers BMW X1. Now here is where it gets interesting. I'll refresh the page and send the hi again. And notice the agent already knows the context from the previous conversation. It doesn't make the tool call again because it already has the answer in memory. This works because we have hard-coded thread ID to 1. So every session picks up the same conversation history from the checkpointer. But there is an important limitation here. The memory only lives as long as the server is running. If I restart the backend and send the same question again, everything starts fresh. No memory, no context, tool call fires again. That's because we are using InMemorySaver, which stores everything in RAM. In a real production app, you would swap this out for a persistent checkpointer backed by a database. That's it for this video. We went from basic LangChain app all the way to a fully working LangGraph agent with streaming responses, live tool call rendering, and conversational memory, all hooked up and running end to end. If this helped you out, please hit the like button. It genuinely helps the channel grow. If you have any questions, drop them in the comments. And if you don't want to miss the next episode where we'll replace InMemorySaver with a real persistent database, hit subscribe and turn on the notifications. Thanks for watching. I'll see you in the next one.